Hello and welcome. Today we shall be discussing the topic of extrasolar planets. So, first of all, what are extrasolar planets? These are commonly also called exoplanets. These are planets orbiting around stars other than the Sun. A star may have one planet or it may have more planets in a stellar system like we have in the solar system. So, why should we study exoplanets? What is our interest? First of all, planets help us in understanding their host stars better. They provide more constraints on the star than the stars alone. And planetary systems throw light on formation mechanism of the solar system and the Earth, which is of interest to us. And of course, the big question is there life elsewhere in the universe? Because we believe that life can exist in principle on planets around other stars. So, these are the motivations behind studying exoplanets. The main question that we shall be concerning ourselves with in this lecture is how do we detect planets around distant stars? Because planets are hard to detect, because stars are a billion times brighter than the planets which are hidden in their glare. Like in this picture you can see the very small light which you can see here can only be seen when the big light in this lighthouse is switched off. And this is not what we can do in a real star. So, we have to find ways to detect planets in indirect methods. There are several methods of exoplanet detection. First is direct imaging, where we try to image the planet around a star directly by blocking off light from the star somehow. Second is through astrometry, that is through precise determination of the position and movement of a star over a period of time which has a planet going around it. Thirdly, timing variations, where we observe the timing of various stellar phenomena and see the variations in those which can be ascribed to the presence of planets around them. Fourth, gravitational microlensing. If a planet goes around a star and the star is already causing a microlensing event, then the presence of the planet changes the light profile of that microlensing event, and this can indicate or prove the presence of a planet. Now, these four are relatively minor methods. Very few planets have been detected by the first four methods. Next comes one of the most successful methods, that is through the radial velocity method. This uses the fact that a star and a planet, as they go around the common barycenter, the star wobbles or moves a bit around the barycenter, and this wobble can be detected by looking at the spectral lines of the star. The other method, which is currently the most successful method, is the so called transit method, where a planet passes in front of a star and causes a minor dip in its luminosity. We shall be mainly talking about these last two major methods in this lecture, but first we shall briefly talk about these first four methods. Direct imaging. So, direct imaging of planets is possible by blocking out light which is emitted by the parent star. This is hard to do, and for the Sun we can do this by blocking out the Sun, which is called a coronagraph. So, for a star also, like you can see in this picture, there is a star here whose light have been blocked out, and then we can directly find these planets which are orbiting around them. This is a multiple star system which is called HR 8799, and very few stars have been probed this way to find planets around them. The next method is astrometry. This is the measurement of precise position of a star and its variation due to the presence of a planet. As a planet orbits around a star, it causes the star also to wobble a bit, because the center of mass of the star does not coincide with the barycenter of the star planet system. If we can measure the position of a star on the sky very precisely over a period of time, then this measurement can indicate the presence of a planet. As shown in this figure, if this is of course a simulation of how the Sun's position varies due to Jupiter as seen from 10 parsecs away. So, if the Sun's position were very carefully monitored over a period of 20 to 30 years, then we would see such kind of a change in the Sun's position on the sky. But this method is only sensitive to large orbits like the Jupiter, and this requires very long observation time. Also, very high precision is required in this method, because the position of the star needs to be measured very precisely, so that this wobble can be identified. The next method is actually a collection of methods called timing variations. First, pulsar timing variations. As we know that pulsars have very regular profiles of their pulses. The pulses come at very regular intervals. But if a pulsar has a planet going around it, then there are slight anomalies in the pulsar period due to the presence of this planet. In fact, one of the first detections of an exoplanet was through this method, but this is a relatively rare phenomena for a pulsar to have a planet, and even if so, a planet around a pulsar is unlikely to harbor life due to the very inhospitable conditions that we anticipate on such a planet. Second, eclipse timing variations. When we have eclipsing binary stars, we can measure their eclipses very precisely, and if one of the stars has a planet around it, then the timing is slightly changed of the eclipses due to the presence of the planet, and by measuring this we can detect the presence of a planet. Pulsation timing variations. There are several kinds of large amplitude pulsators, pulsating stars, whose periods and whose light curves are very regular. However, if a planet is orbiting around a pulsating star, then the pulsation timings also change slightly, and by measuring these pulsation timing variations we can detect a planet. Transit timing variations. We shall talk about stellar transits in a little more detail a little later, but when a planet passes in front of a star along our line of sight, a so called transit or a dip in the stellar luminosity. Now, this is the direct transit method. What we are talking about here is this variation of this transit time due to another planet which is actually not seen in the transit, which is a non-transiting planet. And using this method, multi-planet systems can be tracked by looking at one transit and the variations in that transit to detect other non-transiting planets. The next method is gravitational microlensing. Gravitational field of a lens star can be changed by the presence of a planet. Suppose there is a source, there is a source star here from where the light reaches the observer's eye, but if there is another star exactly aligned along the line of sight, then this causes a microlensing event, as we call it, as light bends around the star to reach the observer's eyes, and we see a typical regular profile of a microlensing event. However, if there is a planet which is going around this lens star, then this planet changes the mass distribution of this lens system, and that causes a deviation or a spike, as you can see here in the microlensing event. Now, using this method one can detect very small planets in wide orbits, because the microlensing phenomena is sensitive to the mass distribution. However, this is not a very convenient method, because first of all this is a very highly improbable alignment. First of all, we need to have a microlensing event which itself requires some alignment of the lens star with the source star, and further a planet needs to be also aligned along the line of sight. And this is certainly non-repeatable, because as the star moves across our line of sight and the planet also moves around in its orbit, this microlensing event will never be repeated. Very few planets have actually been detected using this method. Now, we come to one of the major methods, that is the radial velocity or the wobble method. Now, when a planet and a star orbit each other around their barycenter, the star is seen to move slightly, or wobble as we call it, move slightly back and forth. This happens because the center of the mass of the star is not coincident with the barycenter of the star planet system. As you can see in this diagram, this is of course highly exaggerated. This is a star which is shown in red, a large circle, and a small planet which is shown as this small blue circle. They are both going around this common barycenter, this gray point here, which is the center of mass of the star planet system. Now, as they go around this, the star is seen to wobble around this barycenter. Now, what this causes is a Doppler shift in the light emitted from the star, because as we know that when the starlight comes towards our eyes, if the source, that is the star, is moving towards us, then the frequencies of light are shifted to shorter wavelengths or to higher frequencies, that is called blue shifted, and if they are shifted and if the star is going away from us, then they are red shifted. So, what we do is that we measure the spectrum of the star. We observe the spectrum of the star and we identify some convenient spectral lines in the spectrum of the star. These are absorption lines. Now, as the star wobbles around the center of mass, sometimes it is going away from us and these lines are red shifted, they are shifted towards the red. At other times the star is moving towards us and therefore, these lines are blue shifted. So, we can measure this Doppler shift in the spectral line, and if this shift happens periodically, then we know that it is due to the presence of a planet and therefore, causing the star to wobble. The amplitude and period of this velocity of this wobble reveals characteristics of the planet, and we shall look in more detail in the next slide. So, first of all, if the orbit of the planet is circular, then the radial velocity follows a sinusoidal pattern, as can be seen in these two graphs here. This first one is actually the first planet which was detected using this method 51 Cb in 1995. As you can see that the what is on the x axis is the time of the phase equivalently, that is the phase is calculated by determining the period of this wobble, and on the y axis is the radial velocity. So, the positive velocity and the negative velocity for the two directions of the star's movement along the line of sight or away from the line of sight. This is the similar graph for another star. Now, if this is a circular orbit, then we have a regular sinusoidal pattern. For elliptical orbits, the pattern is different. Here we confine our discussion to the circular orbits. If the orbital plane is not perfectly aligned with us, with the line of sight, like in this diagram, that is, there is a angle of inclination I which is less than 90 degrees. This is the orbital plane where the star is going around. This is the barycenter of the star planet system, and the star of course has a linear velocity v, let us say, but what we observe is a component v sin I along the line of sight. So, we only see a component of the linear velocity, and this has some effect on the results that we obtain from this method. Now, in this radial velocity or the wobble method, we have two observed quantities, namely the period or the p, which is seen in this graph, this distance between these two peaks with time. This is the period, and this is of course the period of wobble of the star, but that is exactly the same as that of the planet, because they are always on opposite sides of the barycenter. The second observed wobble is the amplitude of the wobble, which we denote by the symbol k, that is v star. The linear velocity of the star is called v star sin I, as we discussed. This is a component of the line of sight velocity, or the component of the linear velocity. This is the line of sight velocity. This is the k, the amplitude. Now, using Kepler's third law, we can obtain the orbital radius. This is Kepler's third law, where of course, we have made the approximation that the stellar mass is much larger than the planet mass. So, once we obtain the period, Kepler's law gives us the orbital radius r. Also in a circular orbit, we can calculate the centripetal acceleration of the planet, and that is of course caused by the gravitational pull of the star. Using this, we can obtain the velocity of the planet in this form. So, we can obtain the orbital velocity of the planet from this. Next, we use momentum conservation, that is the momentum of the total star planet system is conserved, and using that we can obtain a measure of the mass of the planet. Now, because of the sin I factor, this inclination factor, we do not really get the mass of the planet, rather we obtain the mass of the planet times sine of the inclination angle I. So, this is only a lower limit to the mass of the planet because of this inclination factor. The radial velocity method actually favors detection of massive planets close to the star. This is because only massive planets can cause a significant wobble in the star, and especially if they are close to the star. So, this results in a bias of this system towards detection of what are so-called hot Jupiters. Jupiter like planets, that is massive planets, and hot because they are close to the planet to the star. So, as you can see in this graph also, where the distance from the star is shown on the x axis in astronomical units, this is 1 AU, and on the y axis is the mass of the planet, and you can see that the large number of planets are more massive than Jupiter in this method. So, this method has several advantages. The main advantages are that this is distance independent, because we are doing spectroscopy here, and secondly, these observations can be done from the ground. We can observe the stellar spectra from the ground. The disadvantages are that this requires a very high signal to noise ratio, because the wobble signal has to be distinguished from other variability signals from the star. Secondly, this only provides a lower limit to the planet mass because of the inclination factor, and this does not work for stars which have strong intrinsic variability. The most major method nowadays is the method of transits, which is called planetary transits. The phenomenon is like this: as a planet passes in front of its parent star, it causes a very tiny, that is several parts per million decrease in the stellar brightness. This is a picture of Venus transiting the Sun, and this is what is a phenomena called transits. For distant stars also, if they have planets which cross in front of the star, then we have the so-called planetary transit. Now, what this does is that as the planet passes in front of the star, it causes a dip in the stellar luminosity, which can be measured by ultra precise photometry. And if this dip is periodic, as the planet goes around the star and comes back in front, then we can detect planets using this method. Now, the occurrence or the detection of transit depends on the alignment of the orbital plane and the line of sight, because if the orbital plane is not aligned with our line of sight, then the planet can be going around the star, but it will not cause a transit. And secondly, the relative size of the star and the planet has to be large enough, or it has to cause a significant dip so that we can actually detect it. So, the planetary transits are seen as a series of sharp dips in stellar brightness. So, this is data from the Kepler satellite. So, the stellar luminosity is measured very precisely in this, and you can see that these dips here, which are very regular and periodic, these are the planetary transits. Each of these dips actually have a U shape like this, and this transit lasts only for a few hours, and the difference in time between two successive transits gives the orbital period of the planet. And once we know the orbital period of the planet, again using Kepler's law, we can get the orbital radius. But there is more information in this transit light curve, which lasts a few hours, and this gives us information about relative size of the planet and the inclination of the orbit. So, the planetary transits have this characteristic U-shaped light curve that we saw on the previous slide. Now, as the planet crosses the stellar disk, when it just enters this region or exits this region called ingress and egress respectively, we have a gradual dimming of the stellar brightness, and then we have a minimum, and then again it increases back to the average brightness as the planet crosses the star. If the planetary orbit is not exactly edge on, but has an inclination, then the planet does not cross the star across its equator, but across a chord like this. Now, in this diagram we have assumed that the stellar luminosity or the stellar disk is uniformly bright, but stars have limb darkening, and this limb darkening effect means that the planet blocks areas of different brightness of the star as it goes across the stellar disk. So, when it is near the limb, the amount of light that it blocks is less than what it blocks when it is at the middle part of the star, and therefore, this causes a curved bottom of this light curve, as can be seen in this diagram, and this is the characteristic light curve of a planetary transit. As we said that there is more information in these transits. First of all, the transit depth, that is the maximum decrease in the luminosity. This gives the ratio of the stellar and the planetary radius. Secondly, the period of the ingress and the egress when the planet is blocking the stellar disk only partially. This gives information about the inclination of the orbit. Now, knowledge of this inclination improves the estimate of the planetary mass if the same system is observed through the Wobble method, where we had an uncertainty in the mass because of the inclination factor, which can be detected from the planetary transit. Now, there can be multiple planets in a stellar system, and each of them will cause their own transits, and only careful analysis of this data can identify each of these several planets. In this diagram, there are 7 planets which are transiting the same star at different orbital radius, and of course, the sizes of the planets are also different. But we can analyze each of them separately by looking at these and identifying the periods of the same planet for each of them. It can also happen that several planets transit the star at the same time, and therefore, the characteristic planetary transit light curve is changed in this manner. When all the 3 planets are in front of the star, then we have the minimum brightness, but when only 1 or 2 of them are in front of the star, then of course, the brightness is higher, but not maximum. But this again can be analyzed through proper modeling of the orbital radius and the size of the planets. We can get more information out of transits. This graph here shows the light curve of a planetary system, which was observed by the Kepler satellite. So, at normal magnification, one can see the characteristic transit light curves, and the distance between them, of course, or the time difference between them gives the period of the orbit. But when we look at higher magnification, we notice that there is a variation in the average luminosity, as well as there is another small dip at apparently the maximum of this stellar luminosity. So, what is happening here? What is happening is that the planet, as it goes around the star, so the primary transit is caused, the primary dip is caused when the planet passes in front of the star. But then as it goes around, the planet also reflects part of the stellar light, which causes this increase in the total luminosity. And then as the planet goes behind the star, then this reflected light is no longer available to us, and we see only the stellar light. Here the planet's different phases, just like the phases of the moon, are shown as it goes around the star. And so, when it is in front, we have the maximum dip, the star's light and the planet's shadow, and here when the planet is behind the star, we get only the flux from the star. So, now that we know the flux from the star alone, we can subtract it from the total flux and get the flux from the planet only. And this is very important information, because this can give us the reflectivity or the albedo of the planet, and this gives us a clue of the composition of the surface of the planet. There are other aspects of planetary transits. As the planet passes in front of the star, the starlight passes through the planet's atmosphere, and therefore, because the atmosphere may consist of different gases, if we observe this planet at different wavelengths, this light at different wavelengths, we will find that the dip is not the same in all wavelengths. As you can see here, at different wavelengths ranging from around 300 to 1000 nanometers, you can see that the amount of the dip as well as the shape of the light curve are all different. And this gives us information about the planetary atmosphere. Further, as the planet passes in front of the star and the stellar light passes through the planetary atmosphere, it can cause an increase in the absorption lines. It can cause an increase because the stellar light is absorbed more in the planetary atmosphere. So, if we observe the spectrum of the star before the transit, during the transit and after the transit and compare them, we get information about the planet's atmosphere from this change in the spectrum. Now, stars can also have star spots, which are also regions of less luminosity on the star. But if a planet during its transit overlaps with a star spot, then there is no extra dimming during that period when the planet overlaps with the star spot. So, the brightness of the star that we observe here actually increases because there is less reduction in the stellar light. So, this causes a spike like this in the light curve of the transit. By analyzing this, we can get information about not only the size of the star spot, but we can also get information about the stellar rotation period, because as the star rotates, the spots on this surface move, and therefore, the planet does not encounter the star spot at exactly the same phase on every orbit. So, that can give us information about the stellar rotation period as well. In general, the Wobble method and the transit method are used together, especially nowadays. The standard method of detection with transits, with the space satellites that we have now, are that once a transit candidate is found, is confirmed by looking at the radial velocity profile observed from the ground. And when we combine the results from the Wobble and the transit method, we have more information, because first of all, either the Wobble or the transit period gives us the size of the orbit through Kepler's law. The transit depth gives us the planet size, of course, relative to the radius or the size of the host star, which has to be determined independently. The periods of ingress and egress in the transit give us the inclination of the planet orbit. Now, this inclination can improve the estimate of mass that you observe through the Wobble method. Of course, the estimate of the planet mass also depends on the mass of the host star, which is to be known independently. But the uncertainty in the mass of the planet due to the inclination factor can be removed from the result about the inclination from the transit method. Once we have the planet size and the planet mass, we can estimate its mean density, and this density is a clue to its composition. So, we can know whether it is a rocky planet or whether it is a gaseous planet from the mean density of the planet. Further, the spectra during the transit provides us information about the planetary atmosphere. The secondary eclipse also gives us information about the reflectivity of the planet's surface. So, all these information put together can help us to characterize the planet better by combining the results of the Wobble method and the transit method. The orbit size along with the temperature of the host star tells us what is likely to be the temperature on the surface of the planet and whether it can harbor life. But sometimes planet transits can be confused with star spots or pulsations, because as the star rotates, the spots on it also rotate, which mimic the light curve of that of a transit. But usually stars are slow rotators, and the planet transits last only a few hours, whereas a star like the Sun rotates only about once in a month. So, the time scales are quite different of the star spot rotation and the transit. In this data that is shown here, this overall modulation of the light is due to the spots, and these sharp dips here lasting only a few hours each are the planetary transits. Stars can also have oscillations, and these oscillations also cause variation in the stellar luminosity. Now, these oscillations can have lower or higher periods in the transit depending on the star. In this example, in this data here, the oscillations have much longer period than the transits. These peaks, these spikes are due to the oscillation, and they have much longer period than the transits. But in a different kind of star, like here shown here on the right, the planetary transit has a period of this, and the stellar oscillation periods are much smaller. So, again the time scales of the two phenomena are often different. However, oscillations and transits can sometimes cause complications in detection of either. Is it necessary that we always observe transits if there is a planet? As we said earlier, no, this is not true, because if the planetary orbit is not aligned with our line of sight, then we will never see the planet. So, we can only have a transit if the planet crosses the stellar disk in front of our eyes. So, it can be shown that this probability is actually a ratio of the diameter of the star to the diameter of the orbit of the planet. So, this is about 10% for very close planets, because then obviously the orbital radius is small. So, this probability is somewhat high. However, for true Earth analogues, that is a planet of the size of the Earth orbiting the Sun at a distance of 1 AU, this probability of a transit reduces to about 0.5%. The question is, can you observe transits from the ground? Now, if a planet like Jupiter passes in front of the star, then it blocks a large portion of the stellar disk. It is about, so the ratio, the relative change in the brightness is equal to the ratio of the areas, that is square of the ratio of the radius of the planet to the radius of the star. For Jupiter, it is about 1% of the area of the solar disk, but for the Earth or Venus, it is about 0.01% of the area of the Sun. So, obviously, in this case, we will have a much stronger dip due to the transit than here. So, this is indeed a problem, and to measure this kind of small dips, we need to observe above the Earth's atmosphere. Otherwise, the variations due to the twinkling effect in the Earth's atmosphere will mask the dip due to the planetary transit, and we will never be able to detect it. Secondly, transits are short lived, they last only a few hours. So, we have to look at the right star at the right moment, but we do not know which stars have planets, and therefore, we do not know when to look. So, therefore, transits need continuous monitoring over a long time, otherwise we may miss the transit. Thirdly, of course, we do not know which stars have transiting planets. So, we cannot look at some specific stars, but if we monitor a large number of stars for a long period of time, then we can hope that some of the stars will undergo transits during this long period of monitoring, and we will be able to detect them. So, all in all, the transits can be an efficient method only from space and long time monitoring. And this is indeed has been done. One of the most successful space missions in recent times was the NASA Kepler mission, which was launched in 2009 and it operated till 2018. It had a 1 meter telescope with a field of view of about 100 degrees square with an array of 42 CCDs. And the field of view of this Kepler telescope for most part of the mission was fixed at only one patch of the sky, as you can see in this diagram near the Lyra constellation, and it continuously and simultaneously monitored 170,000 stars for 3.5 years, and of course, it detected a large number of planetary transits during this time. The most current mission is also a NASA mission. This is a transiting exoplanet survey satellite called TESS. This was launched in 2018. This is optimized for finding terrestrial planets. This has a larger field of view, and this will cover the whole sky, unlike Kepler, over its mission time. But in each field, its observing time is between 27 days to 351 days. Now, all these missions are primarily geared to answer the basic question, are we alone in the universe? Because this is a question that has fascinated mankind since a very long time, and looking for exoplanets is the first step in this direction. So, when we talk of life in the universe, we have to first understand that not all planets can harbor life. A planet has to be in the so called habitable zone in order for it to harbor life in the form of life as we know it. What is the habitable zone? This is a range of orbital distances where the temperature would be conducive to life. So, if the star is a hot star, then obviously the habitable zone will be further removed from the star than it would be for a cold star. If it is an intermediate, then the habitable zone, this green region shown here, is a range of the orbital distances where the temperatures will be conducive to life. That is, primarily that liquid water can exist on the surface of the planet. Now, this of course we are talking only of life as we know on the face of the earth. There might be other forms of life which do not require water, but we do not know of any such kind of life, and therefore, that is a mere speculation. So, the habitable zone therefore changes not only on the distance, but also on the type of the star. For hotter stars, it is further removed; for colder stars, it is closer to the star. If you are closer than the habitable zone, then you are too hot. If you are further away, then you are too cold, and life cannot exist. So, the conditions for life on extrasolar planets are several. So, first of all, we believe that life can only exist on a rocky planet, not on a gaseous planet, but on a rocky planet which has an atmosphere. So, therefore, the size of the planet matters. If the planet is too large, too massive, then it holds on to a lot of gas and it becomes a gas giant like Jupiter. On the other hand, if it is too small, then all the gas escapes from the surface of the planet like Mercury, and even if it is rocky, it cannot harbor life. Secondly, the temperature has to be suitable, that is, the temperature has to sustain liquid water on the surface of the planet. And thirdly, the atmosphere needs to have the right composition, that is, it needs to have the right kinds of gases that are necessary for life. So, the temperature on the planet depends on the temperature of the star, the distance from the star as we discussed. The other factor is the shape of the orbit or the eccentricity of the orbit. If a planet is in a highly elliptical orbit, then there will be large variations in the temperature on its surface, and therefore, life cannot sustain itself for very long. So, nearly circular orbits are necessary, if not perfectly circular, for the existence of life, because only then the temperature will be uniform for a long period of time. The other factor is of course the composition of the planet's atmosphere. If the atmosphere does not have greenhouse gases which can retain the heat from the star, then as the planet rotates away from the star, that is, as night descends on the planet, then all the heat from the star gathered during the daytime will be lost, and therefore, again life cannot be sustained. The atmosphere is extremely important, because first of all it needs to have the right mix of life supporting gases, that is oxygen primarily, and mostly inert gases which are non-reactive. Secondly, the temperature has to be stable, as we already said, so it needs to have some greenhouse gases. Thirdly, the atmosphere must provide a protective shield against cosmic rays, UV rays from the star, meteoroids, etc. All these hazards from outer space. And finally, the atmosphere must also be able to transport the water through rain, otherwise life will be confined in only limited parts of the planet. Of course, this is not a necessary condition for life to exist at all on the planet. So far, the nearest Earth-like planet that has been discovered is around a star called Proxima Centauri, whose technical name is Alpha Centauri C, and this is about 1.34 parsecs from the Earth. The host star, that is Proxima Centauri, is about 1/10 the mass of the Sun, and the planet that has been detected is about 30% more massive than the Earth. The orbital radius is 0.04 AU, so it is much closer to the star than we are, but that does not harm it anyway, because the star is also much less massive than the Sun and therefore much less hotter than the Sun. It is also a rocky planet, but still perhaps life cannot exist on it, because the planet is tidally locked, that is, only one side of the planet always faces the star. So, we will have extreme temperatures on the two sides of the planet, both of which will be unsuitable for life. The best candidate for life so far is in the so called TRAPPIST-1 system. This is planetary system around a star that is around 12 parsecs from us. The star is about 1/10 the mass of the Sun and about 1/10 the radius of the Sun, and at least 7 planets have so far been detected around the star. The initial discoveries were made by the Transiting Planets and Planetesimals Small Telescope TRAPPIST. Additional planets were discovered by the TRAPPIST mission itself and also by other space and ground based telescopes. The planet masses are between 0.4 to 1.4 the mass of the Earth. The orbital distances are from 0.01 to 0.06 astronomical units. So, the temperatures at the planets are estimated to be between that of Mercury and Mars, that is between 150 to 400 kelvins, and all the planets have rocky composition. So, these are very good candidates for harboring life. Of course, we do not know yet whether they have suitable atmospheres and whether there is indeed life on these planets. So far the exoplanet discoveries have the following picture. Right from the first exoplanet discovered in 1989 till now, there have been nearly 4,000 exoplanets, that is confirmed exoplanets discovered so far. You can see that initially most of the discoveries were made through this radial velocity or the Wobble method, and later on, after the launch of the Kepler satellite and before that the Kourou satellite, the number of planets discovered through the transit method has shot up. These two spikes in the graph are due to some major announcements of planet discoveries by the Kepler team. So, a cumulative graph looks like this. So, obviously, the number of planets detected has been growing very sharply thanks to these missions in the last few years. So far we have 4,031 planets as of today, which are confirmed, and there are nearly another 4,000 other planet candidates which are yet to be confirmed. There are about 3,000 planetary systems, that is multi-planet systems, discovered. By way of size, we have almost equal proportions of Neptune-like planets, that is not as large as Jupiter, but more like Neptune. Super Earths, that is more massive than the Earth, but not as massive as Neptune. Then there are gas giants, that is Jupiter-like. These three are almost in our detections have the same number of detections. Terrestrial, that is really true Earth analogues, terrestrial planets are much fewer. But this is of course also a selection effect, because it is much harder to discover small planets, these terrestrial planets, whereas we are much more likely to discover gas giants or Neptune-like planets. So, there might be actually studies show that terrestrial planets, that is Earth-like planets, might be actually numerous in the universe. It is only a matter of time before we start detecting them efficiently. By method, the transit method is the most successful, as we said earlier. It is followed by the radial velocity method, and all the other methods which we discussed at the beginning of this lecture have much smaller success rates, and they are rarely used nowadays. So, if we look at the distribution of planets in terms of their mass and period, that is the mass and orbital radius also, you can say, because the period is related to the orbital radius by Kepler's law. So, we find that most of the planets that we have detected so far have periods between 1 day and 1000 days or a few thousand days, and the masses are more concentrated towards Jupiter or Neptune masses. And clearly, the radial velocity method, these red points, are more biased towards heavier masses, whereas the transit method can detect planets with smaller mass as well as closer to the star. If we consider the question of habitability, we have to look at the mass versus radius distribution. So, on the x axis here is the mass in terms of earth masses, on the y axis is the radius. These lines show the constant mean density corresponding to water, iron and the mean density of the earth. As you can see that there are few planets in this region, especially which have mass close to that of the earth or smaller. There are planets which have density in the favorable range, that is in the rocky range, but they are more massive. And also in the distribution of temperatures, this is the planetary equilibrium temperature on the x axis, on the y axis we have the radius, and there are in this inset you can see the planets which have temperatures between 200 and 300 Kelvin, and this is their radii. So, there are several planets now which are really have the temperatures which are conducive to life and which are also rocky planets. Whether they have atmospheres or not is not always known. So, to summarize, the radial velocity method, one of the major methods, this is successful. This can be carried out from the ground. This can provide the orbital radius and the mass of the planet, a lower limit on the mass of the planet. However, large surveys with the radial velocity method are difficult, because surveys with spectroscopy are more difficult to organize. The transit method is the most successful method now, but for this we require observations from space, or rather space observations are most efficient in detecting transits. These provide size and density of the planets. They can also reveal information about planetary atmosphere, and detections have been possible through large surveys carried out by space-based telescopes. What we find is that hot Jupiters are easiest to detect, but smaller planets closer to Earth size are more common. 90% of solar type stars have planets, and most have multiple planetary systems. Metal rich stars are more likely to harbor planetary systems. Planetary migration and eccentric orbits are very common, which is unlike our solar system, where we have fairly stable orbits and fairly circular orbits. So, the solar system looks like an exception if we compare it to other stellar systems. So far, more than 4,000 planets have been detected, and nearly another 4,000 are candidates at this point of time, and this number will only grow. The first detection of Earth-like planets in the habitable zone have now been made, and now further studies will tell us whether they have atmospheres and other conditions suitable for the existence of life, and future missions will take upon the task of trying to detect signals which might indicate the existence of life on these planets. Thank you.